120. This does add up to 105. I'm grading it out of 100, so you guys will kind of have like 5 points of leeway in case it's like any like little issues or any little errors in there. But that's how I had to find at least like weighted for each individual problem. So a lot of what today is, I'm going to go through that practice exam. I also found 2 more column examples, which I did post on Brightspace also, which I could go through. And if we really want to, we could make up any kind of problem you guys want, any kind of questions. It doesn't matter to me, really. So I'm just going to kind of go through this one. Oh, on that practice, I know I was asked it. Don't worry about, I think it was question 4? Yeah, 4 for both for superposition. Like you don't even need 4 to 5 actually, yeah. Like you don't even need to worry about anything for superposition since I didn't get to lecture that. Starting off, I'm going to do shear moment diagrams. So the one we have on this practice exam is a simply supported beam with a distributed load at a distance here in a sec. So this distance is 1.2 meters, 1.6, 1.2. The points are A, B, C, and D. And then also, at point A, there's a 60 kilonewton meter force going counterclockwise, and then this distributed load is 80 kilonewtons per meter. So all you guys are going to need to do for this one is just solve for the shear moment diagram. So I want to see your entire process behind it and like each of the steps accordingly. So starting off, we're going to find our reactions. So I'm just going to put, so we're going to find our reactions. So we have our reaction force at A, so we have AY, AX here, and then BY. So what we can do is, the first one is relatively easy. We can just sum forces in the x direction. It's going to say the right is positive is equal to 0. We only have this AX force in that direction. So we have one reactional force. We can convert this distributed load into a single concentrated force. So splitting this up, we have 0.8 meters and then 0.8 meters. Then converting this into a single force, all we do is multiply that 80 kilonewtons by that distance it's over, so 1.6. And we get that to be 128 kilonewtons. Next, I'm just going to sum the moments about B here. You could do it for A, it would also work out. Sum the moments, do counterclockwise is positive. All that is equal to 0. The reason I made it counterclockwise is just to have this 60 kilonewton meter force as positive, just for sake of simplicity here. So, all the moments we have, the two forces that cause, not forces, the two things that cause a moment about point B is this 128 kilonewton force at the arm of 2 meters from point B, and then in addition this 60 kilonewton force. So we have, and then AY. So we have that positive 60 kilonewton meters minus AY, so it's opposing the moment that we assume to be positive, at a distance of 4 meters from point B.
Wait, so the moments are summed about B?
Yeah.
why would the 80 kilonewton meters be negative?
This is AY, not 80. Not that 80 kilonewton
Oh,
meters.
AY, my bad.
So the reaction force at 80.
Gotcha. Yeah, my bad.
Good. And then lastly, this would have answered your question, that 128 kilonewtons multiplied by that moment arm, which is 2 meters. Doing the algebra here, we get a sub y to be equal to 79 kilonewtons, and that is positive, so it's still going up. And then lastly, we can just sum forces in the y is equal to 0. I'm just going to say down is positive. So all we have here is negative AY, negative BY, then this is, no wait, yeah, and plus 128. We can plug in 79 here, and then just doing the algebra, we'll get B sub y to be 49 kilonewtons, but also still up. Any kind of questions, at least with just solving for reactional forces and everything? Should just be like a lot of review with statics. So starting off with the shear diagram. Just drop both together here. So we have this as point A, point B, point C, point D, and then similarly A, B, C, and D. So first diagram is your shear diagram, and then your moment diagram. Units for the shear diagram are all in kilonewtons, so you don't have to like put them all throughout the whole thing. And units for the moment diagram is kilonewton meters. Starting off with the shear, everything will start at 0. We have the only force that causes shear at point A is just this reactional force A to Y. So we'll jump up 79 kilonewtons, so vertical. That is 79. There is no change from point A to point C. Wait, what did I do? This is AC. I don't know. AC dB. So no change from A to C here in shear. So straight horizontal line. From C to D, it's a distributed load. So the nature, and it's going downward, so the nature will be in a linear fashion, decreasing from A to D at a rate of 80 kilonewtons per meter. This is at 1.6. So it goes from 79 down to what would be negative 49. There's no change in shear from D to B. So again, just horizontal. And then at point B, there's a positive 49 kilonewton force going upwards. Going at 0, indicating that we actually, this shear diagram is correct because we both start and end at 0 here. So similarly for the moment diagram, what causes, starting at point A, the only thing that causes any kind of moment at point A is this internal 60 kilonewton meter moment. So it's going counterclockwise, so negative here. So I'm just going to say this is at negative 60. No. From here, we can, the slopes or the change in the moment diagram is the area of our shear diagram. So we have area 1, 2, 3, 4. In addition, we have this distance of x1. So area 1 is relatively simple. It's just BH, which it is 1.6 1.2 multiplied by that 79 kilonewtons, giving us 94.8 kilonewton meters. A2 is 1/2 BH. We don't have that distance of x yet, which is b. We have the h though. So x1, so we know that the slope is rise over run. We have the total slope, which was at 80, is equal to our rise, which was negative 79, and our run is at x1 we were trying to solve. It's actually negative 80. So solving for x1 here, we get that to be about 0.9075 meters. So we have 1/2 the base, which is that 0.09075, multiplied by the height, which was 79, giving us for this one 39, and that is kilonewton meters. A3, we can find this distance of x2 by just subtracting that 1.6 minus x1. We get x2 to be equal to 0.6125. So again, same thing since it's a triangle, 1/2 BH. 1/2 the base here is at 0.6125, and then that h is negative 49, giving us negative 15 kilonewton meters. Then lastly, area of the fourth section, just rectangle, so BH here, which will give us 1.2 by negative 49, giving us for the last one negative 58.8 kilonewton meters. So we have our four separate values here, which is the change between those two separate points. So from point A to point C, the increase from negative 60, adding 94.8 linearly, since this is in a rectangular shape. So it will increase linearly to point C at 34.8. So from point C to this distance of x1, which is where the moment will be 0, or the slope of the moment will be 0, we are increasing positive 39. So from 34 plus 39, you'll get to 73.8. This is going to be at a slope of x squared. So this is the slope of x squared. And that 73.8 is at top. From that point to point C, it'll decrease 15. Again, this is still the slope of x squared, down to what this would be 58.8. And then lastly, it'll decrease in a linear manner from point D to B, negative 58.8, ending back down at 0. Any kind of questions with the process behind shear moment diagram too?
So you're like x squared.
That's the slope.
Yeah.
Yeah.
How do you determine whether or not they open up or down? Does that make sense?
So it's an interpretation of like how the shear moment flows, I guess.
Mm-hmm.
So in this case, it's a gradual change from there, so it's not going to be like a sharp one where it'll just instantly decrease from, say, like here, or it'd be like something like that. Is that what your question is? Just double checking.
of like, so I know it's gonna end up at that like 73.8 or whatever.
Okay,
I'm just,
why is it not, what is that? This?
yeah,
Because at the point at which it crosses the shear diagram, the slope of the moment is 0. So even if you do this, your slope here, it's not 0.
okay. Oh, okay, that makes sense.
Yeah. Any kind of questions with shear moment diagram stuff, so I can clarify before I kind of go on to the next problem here?
So for the moment, if it's counterclockwise, it's always negative this way?
Yeah, it'll be counterclockwise.
I always had trouble figuring out how to do that slope thing too. What I ended up doing, if anybody's confused, is just think, you have the most force at the beginning of that triangle, and then when it gets lower, then it starts to smooth out, you have less force. So you start with a big arc, and it smooths out.
That's another way to think about it.
When the distributive load's at the beginning.
Like if the load was like this?
Yeah.
Okay.
And the shear, there's no, you don't start with anything, right? It starts
No,
at
it'll,
0.
it'll always be 0. So like the first step would be always find your reactions. And then that's where your shear diagram will start is the reaction at your separate spot. And then from there you'll find everything else accordingly.
And the concentrated loading doesn't get put on any of the diagrams.
If there's a concentrated load, it acts as a shear at that point.
I mean, how we made the 80 into a concentrated, we don't use that for the diagram.
Correct. You're thinking about it as a distributed load. So if it's a rectangular distributed load, the nature of the shear diagram will be linear. If it's triangular, it'll be squared, which makes the nature of the moment diagram cubic. Neil, next.
I just wanted to make sure when it crosses the plane on the shear one, you'll always in the moment have a top out, right? Like that's kind of the local maximum.
The slope will always be 0. It could be like decreasing to a spot, then going back up if the loading is going upward. But in the case of this, which I don't think I would give you anything that radical, but it'll almost always be the slope at 0. That's the location.
Okay.
Grace?
I don't remember now, sorry.
Okay.
So it's fine.
So everybody's kind of good with this? What I'm looking for?
So if that moment at the beginning is going clockwise, it would be upwards?
This would be upward. So 60. And then that would change the nature of how all of our, like that would change the nature of the shear diagram. Probably got a couple notes there. But yes. Anything else with this? So everybody's kind of good with at least what I'm looking for shear moment diagrams on the final. Ideally, I like, if it's nice and neat and in this kind of process, keep everything do really well on it, I guess.
Would we have to worry about like the cubic, like having that square slope and the shear moment?
Let me look.
Okay.
Because I can find at least the final way, so what I broke it down from. It's in, I actually physically have it in my office, but I forgot to.
Where is your office?
You guys are gonna break it. It's in ASAP.
410.
It's actually not.
We're getting closer.
It's 406.
Pretty sure, it's
So like right after the elevator, you take a right.
Get broken.
Yeah.
Just break into every 400 office.
The entire floor.
No, there's no triangular distribution.
Oh wait, I know this thing has gone on his thing.
So,
On his office, it has gone.
but
This is on
it's
his-
locked, so if I see it broken into, I'm
You
failing
can
all.
fail all of us.
Yeah. So just making sure everyone is good with this stuff here. Any kind of more questions? Anything else? I can go over another one of these later after I kind of go through at least more circle and combined loading. If you guys would like, or we can go over more columns and then combined loading. Whatever's good. So I'm gonna erase this. Next one.
I might run out of paper. I almost perfectly predicted this class. Let's see. I have a extra page edit. Nope. I mean, I was just
circle one I have on here. The shape I give you. So our stress state with our y x-axis, our loading on this is 10, and then 45. This is all you get. And then we also have 30. And what I'm looking for is the three components of plane stress on this, or the plane stress on the element. So I'm just going to do a plane stress state. And then using Morse circle, I want to find T tau max absolute. So starting off with the first one, all we want, so looking at this, in accordance with our axis, 45, both 45 and 30 are positive, because there's tension, and in any kind of element we will typically consider as positive here. So both of these, the 45 is causing tension in the y direction, the 30 is causing tension in the x direction. This shear is negative. The big one, or at least how I've always interpreted it, is I will look at predominantly this x-axis when I'm trying to figure out if the shear is positive or negative, and then the corresponding one about the top. They're going in the same direction, it will be positive, opposing each other negative. That's how at least I've always interpreted it. If you guys got another method of how to do it, by all means go for it. So part A, so we know that positive, positive, negative. So literally all I'm looking for in part A in this problem is sigma x is positive 30 megapascal. Sigma y is equal to positive 45 megapascal. And then tau xy between the two is negative 10 MPa. So we have, part A was relatively simple and straightforward here. So next step, what we can do is start trying to find our absolute max shear. We have, I'm going to take the average between the two just to get our, what would be our center or point C between these. So we have our tau average, which all it is 30 plus 45 divided by 2, giving us 37.5 MPa. So we have our three separate coordinates with regard to Morse circle. We have point A, which is these two combined, and point B is the x, the stress in the x and the shear combined, and then the point B is the stress in the y and the shear combined. So for point A, we have it as positive 30, and then since the shear is negative here, the first one will be 10 going clockwise, plus an MPa, so point B. Similarly, we have 45, 10 going counterclockwise. Then we have our center, or point C also works here, so which is at 37.5 when the shear is 0. So creating more circle here. So we have our shear, and then we have our stress. I'm going to start off at putting point C. Well, let's just say point C is, this is at 37.5. Point A, which is 30 and 10. This top is clockwise, bottom is counterclockwise here for the shear. So let's just say point A is over here. That's point A, which is 3010. And then point B, let's just say somewhere down here, which is at 4510. And drawing a line between the two, we have our stress, our state, and then creating the full Mohr circle between everything. I'm not going to grade you on your artistic ability, so try and make it as close to a circle as you can. So we now have sigma 1, sigma 1, sigma 2. When we were talking about like our absolute shear is our radius with regard to it, but that's with regard to the total state because our absolute shear may not necessarily be in this element. So when we first introduced like the 3-dimension or any kind of the third dimension of it, we have our 3 separate straits of this. So we have between the Mohr circle between sigma 1 and sigma 2. We have between sigma 1 and 0, and we also have between sigma 2 and 0. I'm gonna solve. I'm first going to solve for this radius here. So this radius r. Pulling this over. So r. We have our height here, which is 10. This is a right triangle. And we know that this spot is 30, 0 coordinate wise, 37.5, 0, and then 30 and 10. And then these are all just the coordinates with regard to a right triangle. So the center, we know that this distance is 30 from 0 to 30 to 10. So this distance here is 7.5. So we can solve for our radius. So just using Pythagorean theorem. So we have 7.5 squared plus 10 squared. Radical of all that, we get our radius to be 12.5 MPa. So from here, we can solve for both our sigma 1 and sigma 2. So sigma 1, all it is r plus the average. Which our radius is at 12.5 plus our average, which was this 37.5, giving us 50. So we can similarly do sigma 2 here, which is sigma average minus the radius. In the case of this problem, we actually don't necessarily need to solve this, because if we're thinking about, with regard to the absolute max, we have between sigma 1 and sigma 2, which is this Mohr circle. We have between sigma 1 and 0, which happens to be this Mohr circle. As ugly as it is,
Blob.
that's really bad.
Mohr's blob.
The Mohr's potato, more like. Guys, not even better. And the last thing we have between sigma 2 and 0, which is, I'm just. That's more like an egg at this point. Okay, whatever. Our absolute max isn't actually within the original Mohr circle we have. It is this large one, which makes it out of plane here. So we can find our max radius, or our max here, to be equal to sigma 1 over 2, so just 50 divided by 2, giving us 25 MPa, which equals our tau. Okay. Any kind of questions with this one right here? How'd I got this? It's this radius. It's the radius of the big circle here. So what we were solving for was the absolute maximum shear, which when I was talking about Morse circle could not necessarily be in the plane of that element. So that's what we were solving for.
So that is sigma 1 divided by 2.
Yeah, because it's the radius of the big one. Between sigma 1, which is the largest number you have, and 0. So the radius of the big circle there.
So, sigma 2 was like negative 60, would you use that one instead? Or no?
Typically, you want sigma 1 to be the larger number between the two. If it's negative 60, it will change up. It'd be, so if that's the case, so sigma 2 is like negative 60 like you said, the absolute max will actually end up being the radius of the circle. And it'll be within the element itself.
Near your sigma average, is that a 20 or a 2? It's a 2, by the way. Plus.
Which one am I looking at?
37.5 sigma average. No.
Left, yeah, go. That 30,
Denominator.
yes. There you go.
Yeah, good job. Good job.
Are we gonna have to do the rotation thing?
I'm looking right now.
Yeah.
So when it says principal is
We're gonna do rotation if it sucks. That's what I get stuck on. But this isn't terrible. I got stuck on the theta average because it didn't explain it in I was looking at online, but now it's explained.
Yeah.
No,
So
I'm not rotating the element for you.
Okay.
Wait,
But
really?
Wait.
make sure you understand how to what that angle theta represents between it. It's something I'm asking for.
So for points, it would be how you determine the arrows, like which way?
So
if
if this, it's always, it's with regard to your shear here. It's actually stuck on the side, but if this
we almost got
is
bonus points.
negative, point A will be clockwise, if it's positive, it'll be counterclockwise. So A, at least this is some of how I thought about it, you'll have for each one that respective number. And if the shear, can you actually represent this well? You'll have if your shear is positive and if your shear is negative. If it's positive, it will be counterclockwise, and if it's negative, it'll be clockwise. And the other one is a split.
Sorry. I understand everything's going on. I just, when you decide if it's positive or negative, I still don't understand. So you take the x-axis and the top of it is going in the opposite direction?
That's how I mean, it's me
And
personally.
that's just where, like if the 10 was located up top, then you would look at the one at the bottom of the square?
Are we thinking about shear here?
Yeah, like let's say you take that 10 and you put it up top in the other
Oh,
corner.
it's the same thing.
Then you just look at the bottom of
No.
the square.
I mean, this could be either the top or bottom. It's just showing the value of this shear.
So you just compare the x-axis to one of the lines?
I always
So-
compare the x to the top one, and if the directions are opposing, it's negative. If they're in the same direction, it's positive.
Okay.
Wait.
There's no bearing on where I have just this. It's just an indication of what the magnitude of that loading for this shear is.
Okay.
I was gonna say, the way I'm able to like see it is I can look at it kind of in quadrants. There's 1, 2, 3, and 4.
Yeah.
If it's pointing toward the second and fourth quadrant, then it's gonna be negative, and if it's first and third, then it's positive.
Yeah.
That's just for the sheet.
Yeah, so everyone kind of has their own way of visualizing it. That's the one that this helped me the most. So like if our axis was this, if our x-axis was in this direction, our y was still vertical, this shear would then be positive.
Yeah.
Yep.
I'm pretty sure I'm not being.
Why shear is positive versus negative? Okay.
It's just for that negative 10 ones and negative and positive.
Any kind of question with
The arrows.
anything with more circles?
For that axis.
The other ones are just tension and compression, right?
Yes. So, to figure out if your Y and X stresses are positive or negative. Anything else with this one?
And for the coordinates, to determine whether the shear in the coordinates is positive or negative, you just,
This is how,
oh, I see, okay, I see,
it's
okay.
kind of like this. If the shear is positive, point A will be counterclockwise. If it's negative, it'll be clockwise, and then the opposite of point B.
Okay,
The way I've looked at it is if you have, you like dedicate like two sides as A, two sides as B, and if it's like twisting
Yeah.
this way, it's A, or like it's rotating clockwise, and the top is going this way, it's rotating clockwise.
Okay.
I don't know if that's.
If it's consistent and it's correct with it, if that's how you think about it,
That's
then
how,
then use it.
that's how Grove was showing that,
Okay.
on the video. When I was watching it.
Yeah, so that's how, if that helps you, by all means do it. Any questions with at least this problem or anything with more circle? Pretty straightforward, right? At least I hope.
So just.
Next one will be, next problem I'm gonna go over is combined loading.
I just wanted to make sure I grabbed it because. I wrote down the old one. Yeah.
Do you have the quizzes for the combined loading? I thought I gave them back to you guys. Yeah,
the one with the sign, yeah, you give back.
I thought I gave
Yeah.
those back to you guys. Like, yes, on yesterday, actually.
Yeah, yeah.
Yeah. Indeed.
I also posted that
Take it
solution,
back.
like, online under the review. Here, guys, it helped.
Yeah, I saw the Rick roll, so, yeah, thanks for
I
that.
figured some people would
Yeah,
appreciate that.
I like the dedication to finding a no ad video too.
Well, ideally, I wanted to find one was like an MP4 without like anything in the title. But I thought, man, I'm like, oh, this is even easier.
Yeah, there's like a link.
Okay, so combined loading. So, again, bear with me, my artistic skills are extremely lacking. We have basically a pipe system, almost at like a T-joint where it is fixed at this location. We have our axes are, we have the Z-axis, we have our X-axis, and then we have, oh god, what kind of line was I drawing? Our Y-axis. We have 3 separate points of loading. So we have 55 newtons. Really press this. So along the Z-axis, I'm not going to get distances here in a sec. We have a. God, all these pens suck.
Well, Chris isn't here to give you any new ones.
Yeah, I know. I stole this one from in here. This is one that was already in here.
I was gonna say, check the other classrooms really quick, they're not gonna be using them.
There.
I'm not here.
So we have 90 newtons. This one is along the X-axis. And then we have 120 newtons. Distances between everything. So this distance is 225 millimeters. the same as this distance. We have, what we're looking for, we put this on now, is at point H, which is approximately here. And I'll kind of give the coordinates of it here in a second. This point H is, we have two more distances. So we have between this corner and H is also just 250 millimeters. Distance between this corner and this 120 loading is 300 millimeters. And then lastly, between this loading and the fixed end is 175 millimeters. And what we're looking for is all components at that point H. So all the components at point H. The coordinates of it are, so we have along the x-axis is 0, along the y-axis is 25, and then lastly along that z-axis it is 225. Any questions with the setup of this?
I want to ask, like, the coordinates on the actual diagram, is the x
It's
of
with regard to this fixed end. So that's where the coordinate system originates.
Okay,
I want to make sure I'm not being tricky with you guys here.
Is that 250 meters to H?
so,
From which side?
Um,
From that corner?
yeah, from the center line to H, is that 250, the distance?
Yes.
so I'm just confused on where the,
Don't worry about the coordinate stuff.
Okay.
The final. I give you the cross section.
okay, cool.
Okay.
Is that 175 in the z direction?
This one?
Yeah.
Yeah, it's the one that's the axis. So since we're trying to determine the state, actually, any kind of questions again with the setup before I really start going with it? Okay. So we're trying to find that all the components of the state stress at point H. With regard to the coordinates, since the y is our vertical, we can actually find what both our radius and our diameter are from this, so we can find that the radius is the same as the coordinates, which is 25 millimeters. Our diameter is just double the radius, so 50 millimeters. The first big step whenever we do any one of these combined loading problems is we're going to take a cut across this area of interest where we're looking for all those components of stress. So in the case of this problem, we're going to take a cut directly at point H. And then we're going to be given two separate free body diagrams to work with, both either the left and the right side here. So I'm going to first draw the left one. So we have vertical, almost like a T shape. We have our loading. I'm looking at another of
He's taking. Comes back with. Isn't there one at the top?
Yeah, there is one at the top, right by his water bottle. Cam,
Yeah,
look
because
next to your
it's
water bottle.
split, so like this is,
The
and then
other
this
water
is
bottle.
one
Other water
thing.
bottle.
Okay,
Up
so
at
Might
the
not
top,
be
there's
yours.
a red there. There's a red one.
The red one.
Hopefully it's decent.
This was not dead. Oh, it smells strong. I just like opened it, I got like a big whiff of it. Okay, that's a little better. So we have 90,
On the magic marker.
Yeah, there we go.
90 newtons. We have 55 newtons. We have our different distances. Both of these were 225 respectively, all in millimeters. And then we also have the distance between this T and this, what we took as cut, which was 250 millimeters. Across this cut, we have all our different states of stress, or our internal forces. So we have our axial force, or our P, which could also be noted as our force along the z-axis, and then we have our corresponding force along the y, and then our moment along the y. I'm going to switch the arrow. No, wait. This is force in the y and z. X. I'm going to flip the arrows, just keep it consistent with the problem. I have, so our force in the y direction, our force in the x direction. Then in conjunction, we also have our moments. So we have our moment about z, moment about x, and moment about y. Big boy. In addition, we also have the free body diagram of everything from this cut over, or the rest of the structure, which all that one is the rest of the shaft to the fixed end. We have that loading of 120 newtons. And then we have the similar distances of, this was 175, and this was 50. Then also similarly, we need all our internal forces. So we have our force in the z, force in the x, and force in the y. So Fy. And then we have all of our different moments. So we have our moment about z, moment about x, then moment about y. Any kind of question with how I want the free body diagrams and everything?
Can I take a picture of that real quick? Yeah. Go behind the thing.
Sorry. Would it be easier? Could you read this better? Or since my handwriting is on this.
No, I've been doing fine so far.
Oh, okay.
Is that the directions of moments in both diagrams going down?
So you have one in each. This is just.
This one should be up.
But this way.
They should oppose, they should oppose each other at this,
One in the X, one in the Z.
yeah, moment about y. It doesn't matter, like, on the exam, it doesn't matter which direction you have them, as long as they're opposing
One
each
Z,
other.
not in the Y.
But typically, the axial force, or the force coming out of the cross section, will be pulling away from it. And then the corresponding,
There is no Y.
in this case, Fy and y, and then Fx just need to be opposing itself on the corresponding side.
In the X.
Why don't you just make the 120 at the moment?
This one?
Yeah.
What's actually interesting about this problem is we don't even need to worry about this 120.
Yep.
Okay, because we can just take, God damn it, this one died too. I have such bad luck with these. We really can only take this side to do our entire equilibrium and final state of stress at that.
Okay.
Across this entire thing, so we don't even need to worry about this 120. So using only this left side and these external forces, I'm going to start off by finding my force in the x direction. So sigma fx is equal to 0. I'm just going to have, so the right is positive. We have negative fx and positive 90. So negative fx plus 90. We get this force in the x direction to be equal to 90 kilonewtons. Sum of forces in the y is equal to 0. I'm going to have downward as positive. We only have our force in the y direction here. So we only have Fy giving us f of y is equal to 0. And then lastly, forces in the z is equal to 0. Just going to do along the length as positive. We have negative f of z here. And then we have that negative, in this case, 55 newtons, giving us force in the z is equal to negative 55 newtons. So we have our three forces. Next, we can do our moments. As what I do with a lot of these, I'm going to take it about the centroid of that cross section, or the center of it, as a point O. So, point O. I'm going to sum the moments at point O about the x-axis. I'm going to do the right is positive. All of that is equal to 0. We have this negative mx opposing what we have assumed as positive, so negative mx. Interpreting what causes the moment about point O about the x-axis, so thumb along the axis here. I'm just going to put it along with m of x here. Curling our fingers, so what causes this entire structure to rotate this direction, you could say. This 90 kilonewton force is in that x plane, so we don't even need to worry about it. It wouldn't even it wouldn't even cause any moment about point O anyways. So the only thing that causes moment about this x-axis is this 55 kilonewton force at a moment arm of, I'm going to convert this to meters, but 0.225.
Is it 55 kilonewton or newtons?
Newton.
Okay.
Yeah, it's Newton. I may have accidentally said kilonewtons.
I was just making
So
sure.
are
'Cause I
all
realized-
those on the right? All of those
Newtons.
are newtons or? Okay.
Oh, is it 9 supposed to be? Okay.
It's supposed to be Newton here.
I was getting confused. I was like, is it-
I wasn't increasing the magnitude. I'm sorry. So, I'm assuming positive, or what's a positive axis? Positive here, negative moment, curling our fingers. This is opposing what we had as our positive axis for the initial problem. So, this will be minus 55 newtons times the moment arm, or the distance between this moment between the axis and our force, which is this 225 millimeters. I'm just going to convert it to meters, so 225. And this gives us a moment about x to be equal to negative 12.375 kilonewton meters. So,
Newton meters.
God, why am I doing kilonewton? I have done a lot of newton meters. Next, I'm going to do point O with respect to the y-axis, just positive is upward. Moment about y is all the other one in that one, so we have our is opposing what we assume to be positive, negative my. Now again, using the right hand rule, putting our thumb along where our axis is, curling our fingers, so what causes this sort of like almost like rotate about that point O? This 55 kilonewton force, since it's acting along the plane, doesn't cause it to curl at all or any kind of moment. This 90 kilonewton, not kilonewton, Newton force, I need to get that in my head. Newton force does, and it's at the moment arm of this 250 millimeters. And it's positive 90 newtons and then 0.25 meters. We get our m sub y to be equal to 22.5 Newton meters. And then lastly, we're supposed respect to the z-axis, along the way, we have this moment about z is opposing what we assume to be positive when we're doing this equilibrium equation. So negative mz. Doing the right-hand rule again, putting along what would be like the length of this T section, curling our fingers. So what causes it to rotate about it? This 55 kilonewton force is in the plane of it, but this 90 Newton force causes moment about it. And it is positive in this case, so 90 newtons multiplied by that moment arm, which is 0.225, giving us our moment to be equal to 20.25 Newton meters. Any kind of questions with any of this, or the right-hand rule, everything that goes with it, to find all your internal forces?
Are all the measurements, those are in millimeters on the graph, right?
Yeah, I'm just converting it to meters here.
Okay.
How does that 55 affect the moment and y?
So it is a force about the z-axis, or in the z direction.
Yeah.
When you're calculating your moments, any kind of forces in that same direction is nullified because it doesn't cause any kind of moment about it.
So
For the
when you drew it as
y.
in his free body diagram.
Oh, for y?
Yeah, when you split them, he has them.
Yeah, when he split them, so that's
So,
the assumed direction.
If,
So when he has his
Say-
margin on his equation. it's
say my
not
shoulder is the
zero.
end of that T,
But
the rest of my arm
free
is,
body diagram
is
going
the-
down,
that
it's
entire
not
leg.
value.
Yeah.
so thumb in that direction, curling it, this 55 kilonewton force is only pushing on it, and not causing any kind of moment or rotation, or causing my arms almost
Free
like
body diagram.
my whole body to
So the
rotate
same
at that
directions
point.
are inward.
Was it help explain a little?
Yeah.
Okay.
Equations are
Is that an MY at the flat for MZ, or should it be MZ?
It should be MZ.
Down below.
MZ, yeah.
I think I said Z, maybe I said Y.
Alright, and you're just using the right hand rule to find out the positive and negative.
Yeah. Just use the right-hand rule for everything on moments, especially here. It'll make your life a lot easier. Okay. Put that over here. I'm going to start with our stress. So I'm going to first find out area and then our I. So our area of the whole thing, which is just pi r squared, which we just have as pi multiplied by the radius. I'm converting this to meters here. 0.025 meters squared. We get our area to be 1.963 times 10 to the negative 3 meters squared. I sub x, since it's a circle, it's also equal to I sub y, which is just pi over 4 r to the 4th. And that is just pi over 4, the radius, which is at 0.025 meters to the 4th. We get that to be 3.068 times 10 to the negative 7th meters to the 4th. Then lastly, our j, since it is a circular cross section, is equal to pi over 2 r to the 4th also, r to the 4th, since it's a solid circular cross section. And all this turns out to be is pi over 2 multiplied by that radius again, which is 0.025 squared. We get this to be 6.136.
Who's the radius to the 4th or square?
It's the fourth,
It's to the 4th.
Okay.
the second one.
This one?
No, like that, you
Oh,
just wrote it.
this is the fourth.
Yeah.
Times 10 to the negative 7 meters to the 4th. So we have all our properties of our cross section. Breaking down what causes our stress, what has been consistent throughout all of the problems. So what causes normal, what causes shear. In the case of our problem, our force in the z direction is an axial force, so it will cause normal stress, so F of z. And then our two separate moments adjacent to that, so our moment about x and our moment about y, will also cause normal stress. So we have a moment about x, y. And what causes shear is our torsional moment, or in this case it's our moment about the z direction, and our different transverse forces, so F of x and F of y. Question? Okay. And then, let's see, on over here. Anybody need this up still? The free body diagram of anything? So, reset. So our cross section with regard to point H. So our circular cross section, point H is here, and then our axes, our x and y axes from the diagram. So we had our x-axis, we had our y-axis. So our equations that cause normal stress, so a combination of our axial force and our moments about the x and our moments about the y. So we have our normal stress, z, we have axial force, and we have our two corresponding moments, so x over y, ix, and then m sub y, x over I sub y. So we're looking for point H here, determining whether these are both positive or negative, the moments acting on it with regard to our cross section. So we have our axial one coming straight out of the center. We have our moment, which in the x will be acting. Is this one dying too? So a moment in the x. It's acting in that direction, since we assumed to the right is positive here. Happens to be, we got a negative one, so it'll be acting in that direction.
Just like
Moment in the y is acting upward. So assuming, I'm going to start with the x. Actually, starting with our y. One way to think about putting our thumb along that y-axis, so assuming a positive y-axis, curling our fingers. This moment is acting on to the left, or on this side of the diagram. We're using the right-hand rule here. Thumb along that axis, curling our fingers. We're looking at what's happening to the left of this, giving us positive. So positive on sub x. Similarly, moment about y, same deal. We're looking at with regard to it's acting below. So we will have this direction as negative. Then all we do from here is just plug and chug, really. So we have our total. We have our force in the z direction, which is at negative 55 newtons, over A, which we got to be 1.963 times 10 to the negative third, plus moment about x is negative 12, 12.375, multiplied by that y distance from the centroid, which in regard to the x-axis is the radius to point H. So 0.025 meters, all that over I, which is 3.068 times 10 to the negative 7th. And then similarly, the last one we have a moment about the y-axis, which is 22.5. The distance in the x direction to point H is 0, because it's actually acting about the center here. So we have 0. And then we have that as I to y, so I to y, y to x equal each other. We have 3.068 times 10 to the negative 7th. This one just turns out to be 0. Doing the algebra for everything, we get this moment, this stress in the z is negative 1.04 MPa.
Bless you.
But in addition, the two that are based on our coordinate system, sigma x is equal to sigma y is equal to 0. So we have all of these so far. Everybody seemed to really at least understand, for the most part, the stresses, at least on the quiz. Where a lot of things the disconnect seemed to be was during shear, especially with regard to how the shear flow works on these.
What's the y of in the second part?
The radius, this,
Yeah.
0.025.
Oh.
So is this distance from the centroid, or this, since this is still 0.0, in the y direction to point H, which happens to be
What was it? That's the 0, 2.
Oh, I totally forgot what we were doing. Okay. I was like, where did you get the circle? Okay. I was lost.
okay. So going on to shear next. Make sure I have everything written down from that. Yep, so I have all our stresses. So going on to shear stress, I'm going to start with, so we have our 3 separate shears, so our torsion, our 2 transverse shear stresses.
Yeah.
I'm going to start
When
with
you're looking at it. Okay.
f of x.
That just kind of makes more sense.
So drawing that cross section,
I think it's not bad.
then we have our point H, we have our axes, x and y. Our shear, which acts, our shear in the x, which acts in this direction, so along the x-axis, so this is our f of x. We're looking at point H, so as it's going from left to right here, when we do shear, when we're finding our shear flow, we take a cut across that section where we're looking at, and then we take either and everything above it, so in this case it's to the right, so everything over here, which will correlate with our shear flow. Now I give you guys this equation, or at least what the shear equation is here. So shear flow of a semicircle, 2r cubed over 3. And we get that to be equal to 2 times the radius, which is 0.025 cubed over 3. We get that to be 1.42 times 10 to the negative 5th meters cubed. So we have our shear flow, and then all we do from there is just plug and chug, really. So tau with about the x-axis and then the z is on a plane is equal to, again, 90 newtons, multiplied by Q, which is 1.042 times 10 to the negative fifth. All of that over I, which we already calculated out to be this 3.068 times 10 to the negative 7. And then B, which is the base of the Q you took. So in this case, it is actually the entire diameter of, or you can do this also, you can just multiply 2 times the radius if you have the radius in here, that's a 0.025. We get this shear to be equal to 6.11 times 10 to the 4th Pascal. And this is the shear in the x direction, about the z-axis, and all of this is with regard to the f of x. Next, I'm going to do the transverse stress in the y direction. So again, drawing our cross section, or more like potato again. Point H, our two separate coordinates, x and y. And then this is with regard to our force in the y direction, so the force that is going upward. So this one, which is interesting, when we do our shear analysis, we take a cut on our area of interest. So here it's going to be point H. But with this one, you either cut off nothing or the entire thing. So your shear flow will be 0, giving you 0 shear stress with regard to Fy.
So this will give us,
Q is 0, giving us tau y z is equal to 0. And this is with regard to force in the y. Any kind of question with these two separate ones?
How do you know that you're doing XZ versus YZ?
So the second letter here is always the one coming out of plane.
Right.
So in this case, the z-axis coming out of plane. The first one is the direction at which your force is acting.
Okay.
So this first one, since it's acting, it's our force in the x, it's x, z. This one, since it's force in the y, it's y, z.
Okay.
This is going to clear up some things with regard to shear flow on it. And then lastly, we have our torsional one. So again, I'm going to draw cross-sectional potato, point H. We have our x and y. This is our torsion, so as this thing really f of z at point H. So the shear, for when we talk about torsion, is acting negative to what our positive cross section is. So this is our negative tau x in z. This would change depending on where it is with regard to the cross section, or it'll change whether it's positive or negative where it is with regard to the cross section. So let's say we have another point at, let's just say here, which I'm just going to do whatever, W. With the way the shear flow is acting, this one would be going upward, and then this would indicate a positive shear y, z. This is just like another little thing. I just want to make sure you guys understand whether it's positive or negative of what direction it is.
What's the blue arrow by H?
That's just the direction your shear is acting at that specific point. So if we think about point H with regard to torsion, it's along that outermost edge of it and acting in that direction. So I just wanted to add this in. It's not applicable to this problem at all. I just want to make sure you guys know with regard to how directions go. So all we do for this, so we have this tau xz is equal to negative here. We have our negative torsional force. So negative, this is 20.25 Newton meters, multiplied by rho, which is the radius of 0.025. All of that over J, which I calculated early on, which was 6.136 times 10 to the negative 7 is meters to the fourth. We get this shear stress with regard to torsion to be equal to negative 8.25 times 10 to the fifth Pascal. And again, this is tau xz with regard to our moment of at z, or torsional moment. So from our coordinate system, I've already kind of mentioned it. We have sigma x and sigma y is equal to 0. And similarly, we have tau sub xy is equal to 0. Just from with regard to our coordinate system in the plane. So, lastly, just putting our results together, we have, at point H, we have sigma x is equal to 0, sigma y is equal to 0, y. We have sigma z is equal to negative 1.04 MPa. We have tau xy is equal to 0. Tau yz, the only one that causes any kind of shearing force in the y direction is the force in the y. The torsion doesn't, so it is equal to 0 here too. And then we have our tau xz, which is equal to the sum of those two separate ones we calculated. And we get that to be negative 764 kPa. Kilopascal.
You said that was just adding one.
Yeah, it's the sum of all the ones in that direction. I want to see on the final, like your answers compiled at the end. I don't want to be hunting throughout your entire problem to try and find your answers, because then I'll just get frustrated and not, I guess, grade it a little bit harder, you can say. So I want to see the clear and concise process as neat as you can. I get it, my handwriting's not the best too, but at least making sure you're showing that you understand the process behind everything. Any kind of questions?
There's two.
Sorry, Grace.
So that, why is that f of z in this last diagram in the red? Like, why is that f of z? I thought that was normally a moment.
It's our torsional moment.
Which
And yeah, I would think that's frustrated with how this pen is already dying too. That's your moment about Z. You could also have it as T in your diagram, it'll also work.
Okay.
It means the same thing.
But now I don't think.
And then
Draw circles.
what is the equation you used for tau of xc?
Tweak it.
That is, I'll give it to you, the torsional moment.
Yeah.
So all it is
During our time, can we have this example on the card?
T rho from J.
Okay, that's
It's that equation.
Okay.
You said for tau xz, when you use software, did you add this all? What all do you add up?
I'm sorry.
How did you get negative 76.4 kilopascal?
So we have negative 8 times 10. I'm stealing your calculator. My girlfriend. So it's the sum of both it's the sum of this and this. This is 10 to the 4th, this is 10 to the 5th. So we have negative 8.25 times 10
How much is Q?
to the 5th
Kilo? 1,000.
plus 6.11 times 10 to the 4th equals that negative 7,600, wait, negative 763,000 900, which is, I just reduced it down to negative 764 kPa.
Okay.
Kilos times 10 to the third.
Can we go more in depth on how to figure out whether the moments are positive or negative for the sigma?
Okay, so, if there's any other kind of questions I can answer, I'll go into that
Yeah.
here.
So what I was gonna ask is after you go over columns after this,
Yeah.
if you have time,
What
could you
time?
go over,
We have 40 minutes, we can go over more column stuff too.
well, I would wanna go over like more of the second half of loading to where it's after you write the normal and shear. Cause I get a little lost, so after you get all the some forces and the acts and the moments, then after that, it gets.
So you're comfortable all the way up to there, but then it's an after?
All this stuff is relatively new.
Is this part specifically?
Yeah, most of
Okay.
this.
Yeah.
Anything else before I work on that one? So, one way to think about it is when, this is the one that's actually the most fresh to me. I'm gonna erase this one. When I first introduced combined loading, we had, it was a rectangular cross section. There was a blue pen in the other room.
Just someone give him a Sharpie at this point. Actually, if you use a Sharpie, it can't be taken off for a final.
Yeah.
Someone give him a Sharpie.
Let's just write with a really heavy hand, it's not good for these. Oh my god. So we had a rectangular cross section when I first introduced it. We had a point A, B. We had our axis of X and Y. Does it seem similar at all when I introduced it?
Uh-huh.
So we had our same, so again we had our Z, so sigma Z here. We had our P over A, or force in the Z direction. We have our moment XY over IX, MY X over IY. So, breaking this one down first. For, let's just say specifically point A, because the distance along the x-axis is 0 for this one. So specifically for point A, I'm going to use, assuming a positive x direction, using the right hand rule here, so putting our thumb along there. We're looking for point A here. It is above our fingers, so if we're doing right hand rule, it's going to be in tension at that location, giving us both of these being positive, making them positive.
Okay.
Similarly, we can do for point B here. Thumb along, was this the x-axis? For this case, so thumb along that y-axis, curling our fingers. Even if we're looking at both of these, they'll both be in tension. So positive y-axis, positive tension, giving us this one positive.
Wait,
A lot of it will be more like kind of right-hand rule through a lot of this stuff.
Okay.
Now I'm confused because I thought that the equation itself was negative. So do you just don't include any of the signs until you find the sign of mx and the y and then,
This.
okay.
Okay, so
This is
we're-
when I made sure I reviewed a lot, because
Okay.
this was the one I used when I interviewed for Utah.
Right.
So I reviewed this one time.
so disregard the negative M,
Correct.
Y, okay. So just, you.
And just do it based off the right hand rule.
Yeah.
Okay, good.
Cool.
Does that clear this up a little bit?
Yes.
Yes.
And if it's like, everyone seems to be confused on this, I may just give the signs on it on the final, but try and understand this well. So like if it seems like, again, that's something on my end I kind of communicated poorly, because this stuff is really weird still, even to like me to a degree. If it's something I would give the sign, just be like, okay, that's an issue that I had.
Oh wait, why is so I understand why the moment for the my is positive, but why is x positive too? Because isn't it,
This one?
yeah, oh wait. I'm confused.
Try point A, it'll be intention, so curling out of the page here, intention is positive. If we had a point, say we had a point D down here,
Okay.
if that had another element to it, which would be fun, but curling in our fingers, so rotating about this x-axis, at this point D though, it would be in compression. Flipping this sign would be negative.
Okay. Yeah, okay,
So, does that kind of help explain it?
yeah.
And any kind of more thing I can clarify with this? Any,
How did you get the first positive sign?
this one?
Yeah.
Or this first one?
Yeah, that
A positive axis. So what you put your thumb along, so that'd be your positive x-axis here. So this is your axis, and then this is, you could say, where your fingers curl, if you're using the right hand.
Wait, so for the next one, the positive axis,
Positive y. So I'm going about the y.
oh, I see, I see, I
Curl your
see.
fingers, and then you get it at both points, B and A there.
Gotcha.
It'll be intention coming out of the page here, but at point D, you just signal problem.
So you lay your thumb on the positive axis.
Okay, so everything's positive. Okay, I thought I saw a negative below the positive of the I line, the IX.
Oh,
And so I
yeah.
was really confused. I was like, wouldn't that be negative? Okay. Yeah, those are positive signs.
Use negative though, right?
Which one?
For the second portion.
This one?
Yeah,
Right.
not
I think so.
like
This is really helpful.
the value you plug in for X into that.
If you're going to point D or A?
For B or Y.
So if we're going to B, the distance along the x-axis to point B is actually 0 level, because it's in that same.
Oh, yeah.
And then to point A, it'll be positive, whatever this is.
Okay, so when it says X, you mean like from X to Y?
Yes.
And when it says Y, you mean from Y to X?
Yes.
Oh, okay.
Any other questions with any of this combined loading? I want to go through a problem on columns at least once or twice. And then I can try and go through maybe like a quick bit of this stuff if I have time here. So I went through a column example yesterday. So I posted these also online, but I took them from the book I kind of posted. So, I'm going to double check, just to see double check this problem real quick. Okay.
Very easy to get lost. I also did perfectly.
Okay, so,
I was struggling with that specific thing.
I'm trying to like come up with a problem that's pretty similar to what the final will be. If you can, with the one we did yesterday, when we were comparing the diameter of one, whereas basically you have the same critical value for each one, but you had to find a property of the other one, or a similar property, is along that same kind of lines. So if you guys want me to, I can go over through a problem, another column kind of problem, or I can go through more of the combined loading. Either one.
just
and then
'cause,
we
like-
have time.
I'm gonna just make one up
You're
then.
done with it.
Yeah.
I'm gonna just make one up then.
I'll
Alright,
see.
that's fine.
Relatively
Yeah.
simple.
Yeah,
So,
just use the one from the file.
no, I mean, I have it in front of me, but I'm not gonna use it.
You can change the numbers.
Exact same number, exact same method. No. Okay, we're just gonna do this one together then. So we have one column, let's just say that's fixed free, and then one that's going to be fixed pin. We have a length, 4 meters for each one. Then we also have, what's it cross? I'm gonna use this on cross section. I use this on this one, square sheet. So 5 inches by 5 inches. So our cross section for both of these. Let's make this interesting. So this is 5 by 5. These are meters. These are going to be centimeters, or just half a meter. What is half a meter? Fuck it. And then this one is circular cross section with a diameter of 0.75 meters. So what we're going to do here for this problem is we're going to find which one is better for this 4 meter section. So which one between the two has the better critical buckling load. Between these two, we have, I'll give you guys this on the file with regard to our K values for each. There's different kinds of weight columns are with regard to fixed, free, pin, so on and so forth, fixed. So for fixed, free, K is equal to 2. For fixed pin, K is equal to approximately 0.7. It was like 699 or something like that. 0.7 works here. And then, so when we calculate this out, our effective length for each one is just KL. So length effective equals KL. This is where I'm actually going to need your calculator since I came up with these. So our effective length for the fixed free one is just 2 times 4, which is 8, and then the effective length for the pinned fixed, which is at 4 times 0.7, which is 2.8. So we have length effective equals 8, length effective equals 2.8. These are both in meters. So all we're doing for this, so our equation, this only oscillates once since it's not braced anywhere, so like the nature of this first one will be
Not a
something like this. These are so frustrating. Okay, here we go. There's one. And then this one would be something like this. So both of the n for each one of these will be equal to 1. Won't give you anything harder than 1. So your critical equation, P crit is equal to just pi squared EI over your length effective squared. E for both of these, I'm going to do let's just do 200 dpi. Pascals. So all we kind of do from here is plug and chug. We have our, so for the square, we have pi squared times that 200 GPA times I. I'll kind of explain why I'm not completely solving these in a second. Then we have our length effective here, which would be 8 squared. And also for the circular shape, we have pi squared, again, 200 GPa. I, and then that length effective, which just happened to be 2.8 meters squared. Since all we're doing here is just comparing the two separate critical values, you can look at which this denominator will be significantly larger than the other one, giving us that this, whatever this comes out to be, just trying to save it for sake of time, happens to be the greater of the two separate critical buckling loads, indicating that it will actually take more load than the other one. So anything for column, again, I'll just give it to you, but it would be predominantly interpreting this equation. And then if you remember how we did that, the one from yesterday, we had two separate columns of two different kind of cross sections, and we had it as like pi squared E1 I1 over length effective squared is equal to pi squared E2 I2 over, again, the length effective squared. So even if you have like almost all of these different values, you could even solve for, like if I don't give you the modular elasticity or moment of inertia of one of them, you can solve for it using the other columns if the critical buckling load is the same. So this should honestly be, this should probably be like the only, this and the shear moment diagram should actually be like the two easiest topics on the file.
So that's gonna be like the level of like, that's gonna be the level of difficulty of the class.
Think of the problem we did yesterday. It's basically that difficult.
Okay, yeah.
What?
Which of the two from yesterday?
Second one, because I took that from a final. The one where I had to, you had to interpret. Yes, that. It's going to be about that level of difficulty. Okay.
And so you take those two equations, those are two different, I guess, poles or whatever you call them.
Yeah.
And then you set them equal to each other to find like the inertia if you're given like elasticity.
Yes.
And then if you're given elasticity, you just find them.
Yeah, you can kind of find different values. When we did these,
And you're just assuming they would be like equal, like all the other variables would equal each other? 'Cause
if I would give you like all the other ones, the big one is that the
I
critical,
guess it's because or at least you would be equal on both.
your critical buckling between the two would be the same, so you can make the two equations equal to each other.
Okay.
So, we still have 20 minutes. So do we want to do a combined loading problem? People said they wanted to do more.
Can I ask a question about the end part though, you said like the bottom value, wouldn't that make the,
Oh, it's in the top would be lower than the other one.
right, and so why do we want that?
I just tried to, I came up with this problem.
Oh, okay.
Like, I just didn't have anything concrete, I just came up with it, like, right
Okay.
now. But interpreting between these two, this number will actually be significantly greater than this one
Yeah,
because the denominator is so much larger here. So between the two columns, this one,
so you want a smaller p? Isn't that what that is?
you want a larger P between the two because that's like the critical load is what the column fails.
Okay,
So like out in the field, you want something that could actually like have a higher capacity
right,
for loading than something lower, so it'll fail.
So like a bigger
Less
denominator
likely to-
lets it hold more load before it goes over the specific.
Vice versa.
Yeah.
Other way around.
The
So
other way around.
a smaller denominator, the number will be larger.
Okay. And you want to work that one.
Yeah, for this kind of problem. Or even like out the field. I know you're in electrical, so you don't really even worry about this.
Yeah,
But
so, wouldn't the 2.8 be the best of two then?
yeah.
Okay.
So this one is smaller. The total number at the end will be smaller. I didn't even worry about calculating I here.
So we would assume the circle would be the better of the two.
Yes.
Why did we box in the square? Okay.
I was coming up with, this as a way.
okay.
Okay, is there, trying to think of like a, do you have access to the Brightspace?
Edward? Yep.
No, do you have access to the quiz solution? So I could go through the back half of that since everybody knows what that looked like.
Which quick solution?
The combined loading one?
I only see this.
Oh, I put it under final review.
Oh,
So that would be
I think it's this one.
P12.
the Rickroll. Yeah, P12. It's the combined loading. It is. I was gonna go through this since you guys already know what all this is, and I was gonna go through the shear here.
Okay.
Yeah, if you just skip the first part, yes, you can take that.
Mike doesn't want to carry
Okay, so
this.
skipping everything, so this is skipping everything, so this was the quiz. Why do I keep putting these back up? I just want to throw them back. So this was the quiz we did on Wednesday. Everybody kind of did well, especially with regard to, for the most part, with regard to like where our forces were acting, some of the forces, some of the moments, all that, so on and so forth. So I'm just gonna go like, do you guys just want me to do shear? Do you guys want me to also do normal?
Also normal.
Also
Also normal.
Yeah.
Yeah,
So
that would be helpful.
That way.
doing normal, we had
Perfectly. Last page.
like so. It's like the last thing, and it's just dying on me.
We need to go to drop the dollar
Get
general
CPR.
real quick.
I wouldn't come back. Is this the bad one or is this the good one?
Alright, hey, I have a
That's
Sharpie
it.
if you want to use it.
I know, that's my problem.
Go look it up.
So starting off with,
There's the problem.
this is our ring. We had our y-axis and our z-axis. We had our point D, which was located here. So similarly, in this case, we had our force in the x, or our axial force here, and then our two different corresponding moments, or our moment in the y and z. So our equation is x, it's the side of the plane, is equal to our force in the x over a. Then we also have our m sub y.
Oh my gosh.
It's like the last time we're talking for the rest of the class.
I'll bring them back to the classroom.
M sub y z over I y, and then mz y over iz. So everybody understands how you get these, at least how like where these equations come from and all that, correct? So those are the small ones that are causing the normal forces. Yes.
Yeah.
So just combine all of them.
So in this situation, f of x is coming out of the page.
Yes.
Sweet.
So like the z-axis is up, y-axis is to the right. So first off, doing that right-hand rule stuff, I'm going to start with m sub y. So along the y-axis, a positive y-axis, we're looking at point D, but since it's also along this y-axis itself, it is still going to be in tension at that location, giving us this to be positive. Next, we're going to do z. So our moment about the z, so thumb upwards along the positive z direction, curling our fingers. This happens to be on the right side of it, where our fingers are curling, so it'll be in compression, giving this value to be negative. The values for everything, at least with the way it worked out in this problem, we had our m sub y. So I'm just going to push these values down for me. We had our f of x.
Wait, why is the second one positive? The MYZ? Yeah.
Right-hand rule. So if it's along that same plane,
Okay.
or identical along like where your thumb is, it'll be positive at that spot.
Mm-hmm.
So right-hand rule, curling our thumbs out, even though this is along that exact
What-
plane, we could take that cut, it's going to be.
If it was on the other side, would it be negative, or?
It'd be positive there too.
Oh,
But if
okay.
it's below, it'll be.
And then that Z, you just pointed your thumb towards the Z and then curl like this. And that's curling, is that not curling out of the page?
At that, so
Is,
think about it'll be curling back into the page at that spot.
like,
It's gonna go back into, because it's a slice and a half.
The way I decided to think about it is if you think about it on like a sheet of paper, and you're folding the sheet of paper, if your point's over here, if you're pulling it up, that'd be like tension.
Yes.
And then if it's over here, you would be pulling the paper in on itself, and that'd be compression.
Okay.
That's a very good way to explain it. Okay.
And
So
all of our files are going to be folded in half.
like halfway through the
We're
final,
gonna do
you
like-
guys, like,
Everyone is like,
Gonna make it
people
more
who work here are gonna be
down
looking
low.
like really confused, like, what the hell is going on?
They're gonna see this and then this. So the season compression.
People are gonna be using their arm too.
Yeah, right. So the season compression, that makes it negative.
Yep.
Wouldn't it
Bouncy
be
101.
overall negative? Or is it relative?
Well, which one, this
well,
one?
Yeah. I'm looking at the very first one.
This,
I was
this
wondering.
is the
Yeah.
boom jumping jacks.
So if it's along, that's what Grant asked that question. If it's along like directly that axis itself, it'll still be positive there. Because it's kind of at that apex of where, like, say you were pulling the page out to where it starts to come back into it, it'll still be positive at that spot.
So it's just, if it's on the
are you confused?
Axis itself.
since it's on the y-axis, it's positive?
Yes.
Okay.
So value-wise, actually, I think from our free body diagram, f of x was 0. M sub y was 0. And then m sub z was like negative 19,200 pound-feet. So, since both of these are 0, pretty much completely nullifies that. And then we have, this turns out to be negative 19,200. I'm going to pull the units through just to make sure people know where these units came from. So then converting this down to inches, so we have per 1 foot is 12 inches. And then converting it to kips, I have 1,000 pounds per 1 kip. And then it's at that moment arm, or this distance in this y direction. Wait, no. Yeah, and so. So then lastly, this distance is 2.75 meters. All of that was over about 24.8 inches to the fourth, giving us the stress in the x to be equal to 25.6 KSI.
So that was the answer for the stress.
No. To help clarify some stuff out with regard to the stress at least, especially with the directions. So next, going into the shear, I'm gonna start with the torsional moment, or a moment about x. So we still have that similar ring. We have our y and z. Then we have our moment about x, or what our torsional moment was. We were looking at point D. The outward normal is positive here. The direction in which the shear is going is perpendicular. So this is along the positive z direction. The outward normal is positive here, giving this one to be positive xz. Then all we do is just plug and chug. So we have our shear xz is equal to T rho over J, or positive in this case. Our torsional moment was, I believe this 24. Converting that down to inches, it's just so one, because it's one, it's kip foot, 1 foot per 12 inches, multiplied by the radius, which was 2.75 meters. All of that over J, which was, you can calculate out for a tube, or hollow tube, which happened to be about 49.6, giving this one to be 15.97 KSI. So that's with regard to our moment about x, or our torsional moment. Next, I'm going to do Fy, so our tangential shearing force along the y direction. We have our 2, we have our point D, we have our coordinates of y, z. Since this is with regard to our force in the y, so in this direction. But at point D, when we're calculating our shear flow, you take a cut across that area. And this is that case where you either cut off the entire thing or nothing at all, giving us no shear flow, giving us this tau sub x, y is equal to 0. And then lastly, with regard to your tangential shear being force in the z direction, we have our ring, we have point D, still have our coordinates of both y and z. Take this cut, and then we're looking at the area which is above, which is just the area of this entire ring here. And this is all with regard to our, where's the dead one? You're dead to me. Force in the z. But in this case, when we did our free body diagram, we found that our force in the z was 0. So like from our full free diagram, f of z equaled 0, giving us, we didn't even have to do this equation, so x z is equal to vq over ib, because this turned out to be 0, giving us no shear in that direction. But if we wanted to figure this out, like say this shearing force was some positive number, q at d was equal to 2/3 r outer cubed minus r inner cubed, and you can get like a value from there and calculate everything else out. And then the base b just happened to be double the thickness because it's a hollow tube. Just help clear things up here, and then make sure at the end you combine all your answers together because I want to see them just kind of all together here. Okay? If there's no more questions, that's it. Good luck on Monday. Good luck on all of your finals too.
I only have one question because Jude normally talks about it, and that is some of the unit conversions. I don't know if
If there's certain unit conversions that people are struggling, I'll just put it
Okay.
in. So,
I was gonna say no most of them, but there's times where it's like
a little weird.
6 over, and I was like, just clarify with you, was like, I talked this out and figure out the unit conversion.
2:30 to 4:30 Monday. I could send up an announcement too if people would like to.
I have it in my calendar.